Hello, Eugene. These are the answers to the practical in the workbook called Exploring Forces. The first thing you have to do is to get a pencil case and then just push it very gently, but push it so that it doesn't move, that you're just pushing it, and the pencil case remains stationary. Okay. So what forces are involved in this situation? Well, when you're pushing something, that force is called a thrust. The opposing force, and there is one there, is caused by friction between the surface of the pencil case and the desk. So that's pushing back against your thrust. And it's not moving, the pencil case is not moving because those forces are balanced. In other words, they are the same strength but in opposite directions. So we can draw a force diagram like this at the bottom, where we show the thrust force going from left to right, so like this way, and the balanced friction force is hidden, but it's going at exactly the same strength but in the opposite direction. So, okay. What about when you push it hard enough to make it move? Now, if you it said push it hard enough so that it just moves at a constant speed, it doesn't speed up or slow down at that point. It's just moving at a steady pace across the desk. Well, this is again a situation where those forces are balanced. They're a bit stronger than they were before because you're pushing harder, but because it's moving at constant speed, again, they are balanced forces. Okay. What about when you push it hard enough to make it speed up? You can only do that for a little while, otherwise it'll fly across the room. But just at that moment when it's speeding up, what are the horizontal forces like? Now, horizontal means left to right sort of forces. Okay, it's horizontal thing here. So you'll find it accelerates then, it gets faster. And acceleration is caused by unbalanced forces. And this time the thrust is greater than the friction, so there's more force going this way than there is opposing it. That's why it accelerates. So we say there's a net force towards the right. In other words, the net force would be this way, and the movement is from left to right. So that shows the bigger force there. Notice how I'm just drawing this little diagram here to show the forces. Okay, what about a balloon? The balloon experiment. I'm not sure if you had a go at this or not. It said put a balloon in water and let it float and describe the forces on the balloon. Okay. So when you look, well, this time we're looking at vertical forces, up and down forces, but it's the vertical. Okay. So you've always got gravity pulling it downwards. Okay. So the gravity pulls it towards the earth. And what opposes it, and there is an opposing force because it's not moving, it's just sitting there on the water, it's floating. So there must be some other force pushing back against it to stop it accelerating downwards. And that force is called buoyancy. Sometimes you'll hear it called upthrust. So the balloon is stationary, and so those forces must be balanced again. But they're vertical ones this time, but again they're the same length this way, same length as this one here. Okay. And that's that other force, upthrust, you can call that buoyancy or upthrust. Okay. What about pushing the ball underneath the water? It's a bit tricky to do it with a big balloon. You need a lot of water, but it can be done. And describe the forces. Now this time, again, the ball is stationary, so, and the two forces are thrust because you're pushing it down, and weight as well because it has some weight. So there's two forces going downwards, and there's buoyancy again going upwards. It's stationary again, so the forces must be balanced. Okay, so we're talking about buoyancy and thrust. Now, I didn't mention gravity, or weight, so you should really say weight as well. Okay, but we're just keeping it simple here. I guess a balloon doesn't weigh very much. Okay, but it is still there. Okay, gravity's still pulling it down. What about if you let the balloon go? Well, as soon as you do that, it flings right up, shoots upwards. So that means the weight that's pulling it down must be smaller than the buoyancy that's pushing it up. So it accelerates upwards. It's an unbalanced force situation. So the net force would be an upwards force. That's why the acceleration is upwards. The next situation is a pen. It says hold it above the desk and describe the vertical forces. And it says, so you're holding it, so it's not moving. Okay. Gravity's pulling it down, but you're supporting it with your hand. So there's a support force stopping it from falling. Those forces are equal and they're opposite. In other words, they're balanced. So the pen stays where it is. What about if you drop the pen? Well, obviously gravity's having a big role to play there. The support force is gone. As it's falling through the air, though, the air will slow it down slightly. That's called air resistance. That will oppose the movement, but gravity will be stronger, so it'll accelerate downwards. So a diagram like this is air resistance versus gravity. Gravity is the bigger one. So the net force is downwards. Okay. What about when the pen's just on the desk? It's not moving. Well, if it's not moving, you've got balanced force situation. So there is gravity still at work, pulling the pen down towards the center of the earth, but it's not moving, so it must be balanced by another force, okay? And that force is support force. So we can do our diagram like that. Same length, opposite direction. Rubber band, stretch it and hold it there. Balance forces, because you're holding it there. You're still having to work hard with your fingers to keep it open. It remains stretched. So you're pulling it, so we can call that a thrust force. And there's another force involved, and that's a tension force. So the tension is in the rubber and is opposing your thrust, but they must be the same because it's a balanced force. Nothing's moving. Compressing a spring, same sort of thing, but you're pushing it towards your hands towards each other. So it's called compression and not tension. So you can call your push a thrust force, opposing force a compression force. They're balanced, and you can draw it something like that. Again, these are the same length.